So let's talk about lesson 3.5 today. It's all about symmetry. And we're going to start with reflectional symmetry. When you're typing the word reflectional, it's going to get a little red squiggly line under it. It seems like it fell out of common use more than 200 years ago. But that's the best word I have for it, so we're sticking with it. You'll find some, mostly math books and websites, still use it. But it is a real word, so when you're writing it, don't feel uncomfortable. So reflectional symmetry is just symmetry for which a reflection maps the figure onto itself. It's a line that goes through the figure, and then you can think of that dotted line as a place where you can fold the two halves together that are created, and if they line up perfectly, then they have reflectional symmetry. Another way to think of it is if you look at this line right here, if it's a mirror and you're standing here and you look at it, what bounces back to you would be exactly the same as what you would see on this side. That's why it's called reflectional symmetry. I personally like to think of it as just if it was a sheet of paper that I cut that shape out of, could I fold it in half some way so that it lines up perfectly? You can do this with your notebook paper right now and see that a rectangle has two lines of reflectional symmetry. Same goes for here. If we were to draw a little person here and here, now I'm going to give this one hair. It's balding, I guess. And they're looking this way. They would see in this mirror a shape that, if it were to fall down, would line up perfectly with that. Take a second, look around the room. There's so many examples of reflectional symmetry everywhere. The whiteboard, your windows, your computer monitor. You could fold it right down the middle vertically or right down the middle horizontally, and it will map onto itself. We know that reflections are the capital R, and that's just a saying that to reflect across line M or reflect across line N, the figure would map onto itself. Our second type of symmetry is called rotational symmetry, and a figure has rotational symmetry if its image is mapped onto the preimage after a rotation of less than 360 degrees. The rotation, and then this is our rotation notation. Notice it's the lowercase r. This means to rotate it 180 degrees with the center of rotation at P, and that will map itself, the figure onto itself. So find P, that's where we're going to be rotating it around, and we're going to turn it 180 degrees. That means this point would go here, this point would come here, and so on, and that would map it on to itself. So let's talk about a few of the rules though. For it to have rotational symmetry, we have to be able to rotate it between 0 degrees and 360 degrees. If we go over 360 degrees, well, at 360 degrees, it maps onto itself. So that doesn't really help us, right? Because then, of course, 360 and every multiple of 360, it'll map onto itself. The preimage is your original shape in its original state, right? And what I mean by that is exactly what you're given is your preimage before any rotations, translations, reflections, glide reflections. That is our preimage. Anything I do to it, if I move it, if I disturb it just a tiny bit, I create an image of it in its new state. We're actually going to work with the math behind these, but it's good to start with just the ideas of what each of these symmetries are. And to do that, what we need to do is look at an example. So it says, how many lines of symmetry does a regular hexagon have? When we're asking for lines of symmetry, that's when we're talking about reflectional symmetry. How many lines can I fold this shape along that will map or will fold onto itself? So here, when you see lines of symmetry, let's always think of reflections. And to do that, I just look at my shape and I see where can I draw a line that'll cut it into equal parts. So I would do something like start at this vertex, and generally you're going to go vertex to vertex. And if I fold this over, let's move this onto here. If I were to take this side and fold it to this side, we can use our imagination to see that it would in fact fold on to itself perfectly. So, like I said, start with the vertices, and on this one, we have opposite vertices. That means, like I just did, start at one vertex and draw a line straight through to the opposite vertex. Each line through opposite vertices creates equal halves. But that's not all we can do on a regular hexagon. Regular means all the side lengths and all the angles are exactly the same. We can also draw each line through the midpoints, so that's the points in between the vertices, and straight through. And this will cut it into 6 lines of symmetry. Be careful when you're counting these, and don't count all the way around because you're going to double count the lines. What I mean by that is simply this. If I start here, this line travels all the way through, so this is actually line 1 again. Here's line 2, all the way through. That's line 2. Again, 3. This is my 4th line. This is my 5th line. And then in classic thimble, and maybe you can hear the slight panic in my voice, I didn't do this horizontal line. So we're just going to go ahead and call this our 6th line. Does that make any difference on whether or not we label these correctly? Not at all. But we can see we have 6 lines of symmetry that cut this into parts that can be folded over. I can fold any of these lines and see that it'll fold onto itself. All right, so we know we have a hexagon and it has 6 reflectional symmetry lines. But what does that mean for us in terms of whether or not it has rotational symmetry? So rotational symmetry is directly tied to the number of lines of reflectional symmetry. And if you want to know how much you have to rotate a figure, we're going to look at this expression down here and talk about what exactly it's telling us. And I want you to think about it. Earlier we said that rotational symmetry is how often does it map itself between 0 degrees of rotation. So our rotation must be greater than 0 degrees, but not more than 360 degrees. And if you want to know why that is, let's just look at a circle really quick. I can draw a circle around any polygon. Actually, let me show you that as well. All right, so if I have this quadrilateral, I can draw, we're going oh man. Very roughly, I can draw this circle around it, right? We know a circle has 360 degrees, and we know that our coordinate plane is broken off into quadrants of 90 degrees. So what rotational symmetry is basically saying is, or why it's always between 0 and 360, is because if I start here at the right-hand side of the x-axis, this is 0 degrees. We know this is 90 degrees. We know this is 180 degrees. And we know this is 270 degrees. Here, this is just a repeated position, but it's at 360 degrees. And then this is a repeated position at 450 degrees, and then 540 degrees, and so on. So then the question becomes, if I were to ask you to start here and walk all the way around this circle, surveying everything you see on the way, and I said, thank you for traveling 360 degrees. Now I need you to do it again. You're going to look at me and say, well, I know if I do it again, I'm going to have walked 720 degrees. I'm going to see the same exact thing. Everything's going to be in the same position when I'm in my previous position. So we don't care beyond 360 degrees. And if we don't rotate it at all when we're at 0, that's your starting position. So of course it's the same. And then when you go all the way around at 360, 720, 1080, you're just seeing the same thing over and over. It's like being on a merry-go-round. So you're not getting a new perspective. So of course, if it maps at 90 degrees, then it's going to map the next time I come around at 450 degrees, and we're just going to keep seeing the same thing over and over. And that's just kind of a time waster. So this formula comes from the idea, or this expression, sorry, comes from the idea that I just need to travel once around. And I only need to really look at where my lines of symmetry are. Those are my points of interest. And once I've cataloged all of those, I have nothing else to do. So if I were to ask you to travel along the hexagon that we had in our previous slide, here it is. You start here at 0 degrees, travel in a positive rotation, and we want to know how many degrees would you be at here, here, here. I'm just labeling random variables. That'll be alpha, and we'll just go with that. So at 0 degrees, I would start, and by the time I get all the way around, and I get to 360 degrees, I will have seen everything, every point of interest on my hexagon. So the question becomes, how many points of interest will I have? Well, I'll have 6. So to go around every 60 degrees, right? The whole circle divided by the points of interest, or the lines of symmetry, will tell me how far do I have to travel to get a point of interest. So from here at 0 to x, that means I must travel 60 degrees. Then from x to y, I have to travel another 60 degrees, which puts me at 120. And then I'm going to travel another 60 degrees. That means my z is at 180. This would be 240 to go from z to alpha. And then from alpha to what I'm calling beta would be 300 degrees. And then to get back where I started, it's a total of 360 degrees. So if I asked you, how many degrees do I have to turn? Well, we know it's 60 degrees. And then if I said, what is every position where it's mapped onto itself? I'm going to be at 60, 120, 180, 240, 300, and 360. That is how we determine rotational symmetry. We're going to practice a few more of those before we move on. So let's move on to this one. So here it is again, just like we found. Here are my 6 lines of symmetry, this time ordered and oriented and in ascending order in a clockwise fashion. A clockwise fashion means I'm going from here to here, which is also a negative rotation, but we'll cover that more in the future. But now let's look at an equilateral triangle. I'm going to switch over to my straight line tool. And while I'm doing that, I'm going to ask you to pause the video. And I want you to look at this. And I want you to start with the opposite vertices approach, right? That doesn't work, does it? That just puts me on the line of the triangle. This one puts me on the line of the triangle. And I am not doing anything. Our other option earlier was our vertex to midpoint. That one looks like it would fold from here to here down perfectly evenly. So there's one point of symmetry. Start at this vertex and do that as well. That is definitely a second point of symmetry. And straight through here again. I have currently found 3 lines of symmetry. My other check would be midpoint to midpoint. This is the midpoint. This is the midpoint. If I fold this over, I definitely not covered the entire triangle. Same here. So I can say for certain that we have 3 lines of symmetry. All 3 of these lines, when folded along those lines, or if I fold this triangle along those lines, all 3 of them will create a perfect fold where everything lines up. perfectly. So my question is, how many degrees do I have to turn it just to get it to map onto itself? That is going to be 360 divided by 3, because I have 3 lines of reflectional symmetry. So every multiple of 120 degrees between 0 and 360 will map this onto itself. So if I call this 0 degrees, if I want to map it onto itself, I would have to travel 120 degrees somewhere over here, right? Because this would be 90, and then it would be a little bit past it. So then that would mean this point would flip all the way to here, and you would have symmetry. Then I need every multiple of this, so just keep adding it to itself, not recopying it. 120 plus 120 is 240, and 120 plus 240 is 360. We've landed on 360. That is another good hint that we are on the right path. And these are our rotational symmetries. So between 0 and 360 degrees, when will this figure map onto itself? At 120 degrees, at 240 degrees, and at 360 degrees. At 120 degrees, this point will be here. Now this does say equilateral, and this is definitely not an equilateral. This is an isosceles at best, possibly a scalene. So obviously, graphically, we don't trust our eyes, but we do know through these symmetries that these will map at those 3 rotational points. What about a square? I think this one's actually one of the easier ones. And since I have a tool to help assist draw it, this should make a lot more sense. So let's put a square up. That's roughly a square. So how many lines of reflectional symmetry can I find inside this square? Well, I'm going to start with opposite vertices. So I'm going to go from vertex to vertex across the square. So I found 2 so far. I can definitely fold that. Now the reason I did that is just so I can aim a little bit and make it a little bit more clear. Now here's my opposite midpoints. These are through the middle of each side length, or the median, we'll learn later. And I can see that I can fold this one. If I look at this as my fold, this could come down to here, and they would match up perfectly. And I can do that through any of these. So I have how many lines? I'm going to count them because this is where a lot of times I'll make mistakes. There's my first one, and that one crosses all the way through to here. Here's my second one. It crosses all the way through to here. Notice I'm labeling them on both endpoints, and that's just so I don't double count them. As you get more comfortable with this, you won't have to do it. But I can see now that 4 is my highest number that is paired. So I have 4 lines of reflectional symmetry. And then that means if I want to know how much I have to rotate a square, I'm just going to take 360 divided by 4. And that's just 90 degrees. I think this one's a little easier to convince you. And that's because I can draw a coordinate plane, which you guys already all know is broken up into 4 quadrants of 90 degrees each. And if I put a square on that, well, how complicated do we want to get into it? If I draw a true square, this will be at 45 degrees. Through here, this is y equals x. Right. Basically, it's an absolute value function. This might be a little bit overdoing it. But here, if this is 45, oh, that's the wrong tool, buddy. So from here to here is 45 degrees, right? This is bisecting this quadrant. And then I'm at 90 here, and I want to go 45 more. This is going to put me at 135, which then bisects this quadrant as well. So all of these angles that I'm creating are equal. This gives me a right angle, and I can see that because through our angle addition, our protractor postulate that we had in topic 1, these angles made together would just be 135 minus 45. And that leaves me with 90. So this is a right angle. And we can see that this corner here rotated 90 degrees would just map to right here. And then if I did it again, this one would map to here and to here. So of course my points were that from here at 0 degrees, I would travel 90, 180, 270, and back to 360. I've covered all 4 points of interest. I've also shown a little bit of extra above and beyond. Instead of drawing my square so that the corners line up exactly with the axes, I've done a little extra work to show you and hopefully convince you that these types of rotations work in exactly this manner. But for a square, it's every 90 degrees. The easiest way to do this, though, if you really are having trouble seeing this, is take a pair of scissors, cut out a square on your paper. I'm telling you I'm dead serious. A lot of people look at me like this is a crazy way to do it. Once you have your square, take your pencil and set it right in the center, and then manually grab that top right corner and move it towards the left corner, and you'll see that it'll travel 90 degrees. And then just keep spinning it, and you'll see every time you hit a multiple of 90, you'll have it exactly where you start. Another way that'll help you see it even easier, put a number 1 right here, or any kind of mark, and as you rotate it, when you rotate it 90 degrees, that's from here to here, your 1 will be here. When you move again to 180, your 1 will be here, here, and you'll see that it keeps lining up with itself, and every other time it hits in the exact same spot every time you rotate it 90 degrees. And that is a real world, very cheap, very quick, very easy way to prove to you, or to prove to yourself, really, because I can't do this in front of you right now, but prove to yourself that these 90-degree rotations absolutely do map themselves onto, or the square will map itself onto itself. Here's a funky picture. It's a little weird. It's a flower. We are going to take this as a hypothesis that those are, in fact, reflectional lines of symmetry. Remember, if we're checking that hypothesis, or if we're trying to prove a hypothesis, we can just assume it's true. And that helps us avoid the need to look at this flower and say, oh, geez, is it actually symmetrical? Where would it be symmetrical? Do all the veins line up? No, our hypothesis is we have 5 lines of symmetry. So it's given you there, right, in the first bullet. A line through the center of a petal is a line of reflection. Since there are 5 petals, there are 5 lines of symmetry. That's our given, so we can say it's true. And if we want to know how much we have to rotate it to map it onto itself, well, 360 divided by the 5 lines of symmetry gives us 72 degrees. So every multiple of 72 will line up with and give us our image that lines up with the flower. So here we have 72, 144, 216, 288, and if we do that final one, we've got 360. Let's look at this one. It's a little bit different. So we have no lines of symmetry that can be drawn here. And you say, oh yeah, you can. And that's kind of my initial reaction. But these dots change that so much for us, right? Because if I think about it, if I do my opposite midpoints and I fold this down, this dot will be here. And that's not a perfect mapping onto itself. We can try it this way. I think that one's a little bit easier to see that this is going to come over to here. That will not be a perfect mapping on itself. Opposite vertices. Well, here I might convince you, and I think it wouldn't be too big of a stretch, right? I have one line through here. If I fold this down, this will map. If I fold this up, this will map. So here's the one time that this kind of breaks that rule of 360 divided by my lines of symmetry. And that is why we have a standalone example for it. If you can only draw one line of symmetry through it, then you have what is called point symmetry. And that it means it just has a 180 degree rotational symmetry. And some of you are probably sitting there saying, well, that's not my straight line tool, first off. What if we did something like this? Well, here, you can see those just aren't going to quite line up, right? This is just going to flip to here. This is going to flip to here. And we're right back to really just having point symmetry here. Here is our topic conclusion or recap. Reflectional symmetry is a figure that maps onto itself when it is reflected over a line, has reflectional symmetry. And a line of symmetry is a line of reflection when a figure is reflected onto itself. Rotational symmetry is a figure that maps onto itself when it is rotated about its center by an angle measuring less than 360 degrees, has rotational symmetry. And a figure with 180 degree rotational symmetry has point symmetry. Point symmetry just means we can draw one line through it, and if we rotate it right there in the center point, you can get it 180 degrees, and it'll map back onto itself. I would say pause the video, and I want you to do in the comment section so I know that you completed this, you watched the video, is tell me how many, let me number them for you real quick. This is number 1, 2, 3, 4. And I want you to just tell me how many lines of reflectional symmetry do we have? So number 1, we can say 200. Not the answer, obviously, but I just want you to type it up. Number 2, number 3, and number 4. I look forward to your answers. This is 3.5. Homework is on Savas.